a couple more examples of u substitution. And the examples we're going to look at like, well, what if we're finding definite area, right? Finding area under the curve, like example 8. And it really, the only difference is that at the end we have to evaluate that particular area. But I'm going to notice again, there's a function within a function, so I have this function here, 2x squared plus 1. That's going to be my u, because again, that's embedded in a quadratic, or actually a quadratic in the denominator. And so I'll let that be my u. And so 2x squared plus 1 is my u. My du is equal to what? 4x dx. And notice I need an 8x dx. So I'm going to double this. So 2 du equals 8x dx. Okay. So now this integral becomes the integral of basically 2 over our function, with a du there, and that was u squared. Or it's our integral of 2u to the negative 2 du. Now, I have not put my bounds yet, because both 0 and 2 are x values, right? They live in the world of x. But I need bounds that are in the world of u. So I need to translate those. So then I can easily say, well, here's what u is in terms of x. So if I knew my x was a 0, I could just put in 0 here. So 2 times 0 plus 1 is 1. So that when x is 0, u is 1. So I can input that. So there's a 1 here. And when x is 2, 2 squared is 4. 4 times 2 is 8. 8 plus 1 is 9. I can get to 9. So the nice thing about that is that I can actually get the entire expression in terms of u, and I don't even have to go back in terms of x ever again. So now when I take the antiderivative, it becomes 2u to the negative 1. Remember, we're bumping it up a power. Divide by negative 1, and instead of putting a plus c, I'm going to evaluate it when u is equal to 1 to 9. So then, and again, if you don't like that, u there, so you could think about that is negative 2 over u, because that's u to the negative 1, when evaluated u from 1 to 9. So then remember, it's always like f of b minus f of a, so it's negative 2 over 9 minus negative 2 over 1. It becomes a plus, so it's negative 2/9 plus 2. So then that could be like 18/9 minus 2/9, which would equal 16/9, or you could say is like 1 7/9. And that's it. We don't have to go back and find x and substitute that back in for x, because we're not looking for the general function. We're looking for just the definite area. Okay. Actually, I want to skip that example only because that I want to do another one of the u substitutions with bounds. So give me a second here. Let me find. I know I've got another one in our workbook here. So let me take a look here real quick. Our workbook, and this is definitely like thinking on my feet here. Apologize for not being prepared with this video. I thought I had gotten all of the examples. But I know there's some practice problems. Right there. Okay, so let's go ahead and take a screenshot of these next 3. Because again, I think it's just good to see some of these examples done. Send to the current smartboard. There they are. Wonderful. So I'll come back for example 9 in class, I believe. I think I should. Someone remind me. Right? That'll be a good way for me to test if you guys look through the videos. So let's look here again. I want to do another one with the bounds. And again, looking at x squared plus 1, let's let that be my u. Oops, not highlighter. Well, sure, highlight. Let's let that be my u. So we'll go ahead and, oops, there it is. I'll go ahead and define u to be x squared plus 1. Now the derivative would be 2x dx. Notice we have a 6x dx. So we're going to multiply both sides by 3. So 3 du is equal to 6x dx. So now my integral can be 3 du, and it's u to the second power, which is really nice. But let's change our bounds. Remember, our bounds that we put for here and here have to be in the world of u. And this is our translation. So 0 squared plus 1 stays or becomes a 1. So 1. And then 2 squared plus 1 becomes a 5. And I can now basically get rid of x, not even think about x, and just think about in the world of u. So that becomes u cubed, right? Because it's 3u cubed over 3. Instead of putting a plus c, I'll evaluate that when u is 1, when u is 5. Notice my u's are a little sloppy today. I'm sorry about that. So u cubed is 125 minus 1 cubed. So we get 124. So again, once you get everything in terms of u, which includes the bounds, which includes the function, which includes your derivative symbol, then you have you've successfully translated it into the variable u. You just evaluate. Okay. Let's do this one because it's both trigs and bound. How exciting! Now remember, sine cubed. That's the same thing as sine of theta is a quantity cubed times cosine of theta d theta. So when I look at that integral, it makes it a lot, I think, more clear that the u that we should choose should be the sine function that's trapped inside the cube, because there's its derivative sitting right there. So that's a really smart thing to do. So let's let u be sine of theta, just sine of theta. So our du is cosine theta d theta, which we have right there. So now we are integrating in terms of u. It's just u cubed. And then we want to change our bounds. So like when theta is 0, sine of 0 is still 0. So that one stays the same. And then pi thirds, remember pi thirds is a 60-degree angle. 1, root 3, and 2. So the sine of pi thirds is root 3 over 2. So we're going to change that bound to root 3 over 2. And once we've done that, we really don't need theta anymore. We can focus on u. So antiderivative of u cubed is u to the 4th power over 4. Wow, it is so embarrassing. Like I've never seen such terrible u's before. Oh, I apologize. Okay, let's try that again. U to the 4th power is still terrible over 4 when evaluated from 0 to root 3 over 2. And so this is like 1/4 u, so root 3 over 2 to the 4th power minus 1/4 0 to the 4th power. So that's nice. So this is 1/4 root 3 times root 3 times root 3 times root 3, which is 9. And 2 to the 4th is 16 minus 0. So that's 9/64. All right, very good. And then let's just go ahead and do one more. Again, I just want you to kind of see and practice and work through these problems until you feel very comfortable with them. This right here is a function within square root. It's more than just an x, so it makes it a good candidate for a u. Derivative is 2 dx. Notice we just have a dx, so 1/2 du is equal to just dx. This integral now becomes 1/2, and there's my du, and it's just the square root of u, because u was the entire integrand, or entire radicand. Okay, now how do we get our bounds? Put in 0 for x. 2 times 0 is 0, plus 1 is 1. 2 times 4 is 8, plus 1 is 9. So now everything's in terms of u, including our bounds. And, again, if that helps you thinking about the square root of u, before you do the integral, you could think about it as the 1/2 power. So you bump it up a power and divide by that power. So u to the 3/2 divide by 3/2, and we'll evaluate that from 1 to 9. Well, the 3/2 could become a 2/3. We still had the 1/2. And remember, u to the 3/2, I think I said in an earlier video, like that's the same thing as u root u. Like you have a whole power of u plus half a power more, the value from 1 to 9. Well, 2/3 of 1/2 is 1/3. So I have 1/3 u root u, so 9 root 9 minus 1/3 1 root 1. And that u root u is kind of nice then when you're actually evaluating it. Square root of 9 is 3. That 1/3 and that 3 cancels. That's just a 9 minus 1/3 of 1, which is a 1/3. So you have 8 and 2/3. Or if you wanted to write that as 26/3, I'd be fine with that too. Okay, so U substitution, like I said, is a very, very common and often used integration technique. Now, you might be wondering, well, are there other techniques? And the answer is, of course, right? Because we don't just have chain rule, we have product rule, and we have quotient rule. We have other things that are going to be so hard to integrate. We're going to need a lot of strategies. So once we get into a little bit later in our book, into second semester, one of the chapters is devoted completely to integration techniques. And kind of like a little bit of bad news to tell you is that there's some functions we can't even integrate, at least not by hand. We might need to do an approximation. We might need a calculator. We might need a computer system. And that's really interesting. Like, well, to me, it's interesting because you can pretty much take the derivative of anything that you get thrown at. Any function, you could take its derivative. But if you're trying to undo a derivative, it becomes a lot tougher. So, but that's where it's at. Okay, very cool. So, go back, review if there's any questions. Otherwise, come find me in office hours.